Hello learners, today we are going to start a new series on applied chemistry, and the first topic which we are taking is oils and fats. We will be covering a number of topics under this broad topic of fats and oils, in which we will take up the definition, the distinction between oils and fats, properties of fats and oils, classification of fats and oils, vegetable oils and its classification, fat splitting and its process. We will also discuss in detail the properties like hydrogenation of oils, rancidity, and then saponification value, iodine value, acid value, and so on. To start with, fats and oils are esters of higher fatty acids with glycerol. The esters of glycerol are commonly known as glycerides. Fats and oils are called triglycerides because they are esters composed of 3 fatty acid units joined to glycerol, a trihydroxy alcohol. Oils are generally characterized by being water repellent and insoluble in water. They are emulsifiable and have solvent properties for organic substances. They are emollient and are greasy to touch, have low volatility and are liquid at 20 degrees centigrade. Fats are similar to oils, but being solid at 20 degrees centigrade, their spreading properties are limited. Non-drying oils contain saturated fatty acids, while semi-drying and drying oils contain unsaturated fatty acids belonging to monoolefinic and polyolefinic series. About these kinds of oils we will be discussing later in this lecture. A little of phospholipids, cholesterol, phytosterol, etc. are generally present in oils and fats. All vegetable oils except for coconut oil contain fatty acids having more than 16 carbon atoms. Now we have been using the term fatty acids. What are fatty acids? Fatty acids are aliphatic monocarboxylic acid mostly obtained from the hydrolysis of natural fats and oils. They have the general formula RCH2 whole N C double OH and mostly have straight chain. A few exceptions have branched and heterocyclic chains as well. This is the list of some saturated and unsaturated fatty acids. Saturated fatty acids contain C single bond C, whereas unsaturated fatty acids have a C double bond C. Now talking about the distinction between oils and fats. There is no difference between an oil and fat as far as the chemical properties are concerned. The difference between a fat and oil is merely physical, that is of consistency. Coconut oil and ghee are fat in winter that we all observe and oil in summer. The fatty acids in natural fats and oils have almost invariably an even number of carbon atoms. Now seeing the table, it shows the difference between the fats and oils. The fats melt above 20 degrees centigrade, whereas oils have a melting point below 20 degrees centigrade. Now talking about the properties of fats and oils. Oils and fats are non-volatile liquids and are solids lighter than water and insoluble in it. Oils and fats have no taste, odor or any color in pure state. They are readily soluble in benzene ether, petroleum ether, carbon disulfide, carbon tetrachloride, etc. Because of long hydrocarbon chains, such compounds are generally insoluble in water. Natural odor of some fats and oils, for example butter, coconut oil, mustard oil, etc., is due to some minor constituents. For example, the sharp smell of the mustard oil is due to the presence of allyl isothiocyanate, CH2 double bond CH, CH2 is the allyl group, NCS is the isothiocyanate. So because of the presence of allyl isothiocyanate, we get the sharp smell of mustard oil. Highly unsaturated glycerides in linseed oil or tung oil are capable of absorbing oxygen from the air and turn into a transparent solid. These are called the trying oils. Fats are the richest source of energy as food, giving 9.5 kilocalorie per gram on complete combustion in our system. The energy provided by proteins and carbohydrates on complete combustion is 4.4 kilocalorie and 3.96 kilocalorie per gram respectively. But the composition and characteristics of human fat are quite different from edible fats and oils. Oils feel oily or greasy when rubbed between the fingers, and some of them leave a visibly greasy layer on hair and skin. Sometimes this is not always desirable. Oils spread easily on the skin and leave a water repellent or hydrophobic film on the surface. When agitated with water in presence of an emulsifying agent, they however form an emulsion. Oils can be emulsified with water in the presence of a suitable emulsifying agent to form a system in which the water is continuous or is dispersed as small droplets. The water can thus be used as a diluent to reduce greasiness of the skin or hair. Oils have valuable solvent properties and can thus be used as vehicles either in the emulsified or unemulsified state to bring organic compounds with remedial or other desirable effects into contact with skin. Oils and fats gradually decompose in the presence of light, air and moisture. That is, they become rancid due to the microbial action. On continued exposure to moist air, oils and fats undergo hydrolysis or oxidation. The process is known as rancidification. About this also I will discuss later in the lecture. As a result, oil or fat loses the taste and develops offensive smell. Slow hydrolysis by atmospheric moisture forms free fatty acids. The process can be decreased by decreasing the temperature. Oxidation at C-double-bond-C position takes place by the air trapped in the container to form peroxides. The latter decompose to form a number of carbonyl compounds which are responsible for the bad taste and offensive odor. When a fat that contains a mixture of triglycerides is allowed to heat in presence of an alkali, a random exchange of acyl groups takes place between different glycerides, and then a mixture of glyceride molecule is obtained, which is quite different from the mixture of glycerides originally present. This process is known as interesterification. It is used to modify the physical properties of the oil or fat blend by rearranging the fatty acid groups within and between the different triglycerides. Oils are more unsaturated than fats. In contact with nickel catalyst at about 120 to 150 degrees centigrade and under 50 to 250 atmospheric pressure, oils undergo hydrogenation at C-double-bond-C positions to produce vanaspati ghee, or we can call it as solid fat. When absorption of hydrogen takes place at C-double-bond-C positions in hydrogenation of oils, the C-double-bond-C bonds open up to facilitate absorption of hydrogen. It is also interesting to note that fats or saturated glycerides also react with hydrogen in presence of copper chromite as catalyst to form an alcohol. The process is known as hydrogenolysis. When an oil or fat is reacted with concentrated H2SO4, a change in color is noticed with increase in temperature. The exothermicity is proportional to the degree of unsaturation in the fat or oil. The increase in temperature is generally constant for a particular fat or oil and indicates the purity of the sample. This is called as the Momine test for oils and fats. The amount of iodine absorbed by the known amount of a fat or oil is expressed as iodine number, which is the direct measure of the unsaturation in the glyceride. This iodine number also we'll discuss later in the lecture. Oils and fats undergo hydrolysis with acids, alkalis and high pressure steam to produce glycerine and a carboxylic acid and its salts depending upon the experimental conditions. The hydrolysis of fats and oils in the presence of a base is used to make soap and is known as saponification. Oils with a high degree of unsaturation slowly develop a hard surface film in contact with air. This process is enhanced by increase in temperature and certain substances known as dryers. This process is known as drying. Drying is a combination of various chemical processes such as cleavage of peroxy linkages to form carbonyl derivatives, formation of hydroxy ketone derivatives, free radical initiated polymerization of peroxides, and formation of gel. The gel formation initiated at the top gradually extends towards the inner layers, resulting in the formation of hard compact surface. Now let's do the classification of fats and oils. They can be classified as edible and inedible. The examples of edible oils are cottonseed, olive oil, soya bean, corn oil, etc. And examples of inedible oils are tallow, coconut oils, palm oil, etc. The various edible oils like cottonseed, olive, soya bean, corn, etc. are employed for salad dressing, other table uses and for cooking purposes. The hydrogenated fats for cooking and baking include various vegetable oils such as cottonseed, soya bean, peanut, etc. This is due to the fact that hydrogenation improves the color, flavor and odor of the crude oil. Inedible oils including tallow, coconut oil, palm oil and certain greases are used for making soaps. These drying oil industries include paints and varnishes constitute about 10% of the oils. Castor, linseed, soya bean, rapeseed and cottonseed oils are also used as plasticizers for lacquers and polymers. Such oils have also been used for many other purposes as in the manufacture of lubricants, greases, various polishes, creams and emulsions, etc. The important oils of this category called vegetable oils are castor oil, cottonseed oil, coconut oil, soya bean oil, hemp seed palm oil, peanut oil, rapeseed oil, tung oil, etc. The two general methods for the manufacture of vegetable oils and fats are expression and solvent extraction. The method of solvent extraction is, however, widely used. Now let's do the classification of vegetable oils. Depending on the nature of carbon chain, they can be classified as non-drying oils, semi-drying oils and drying oils. These terms refer to the behavior of the oils in contact with moist air, usually in diffused or strong daylight. The drying oils form a firm layer when exposed to the air. The semi-drying oils, however, they make a film but that is not so firm. The non-drying oils do not change much in consistency. In non-drying oils, the carbon chain is saturated. These oils are quite stable at ordinary temperature but become viscous at higher temperature. Examples are castor oil and olive oil, etc. These oils are mainly used as edible oil for salad preparation, soap making as illuminant and for lubrication purposes. Castor oil is also used as purgative for making transparent soaps, leather processing and for lubricating marine engines. Semi-drying oils have some degree of unsaturation in the carbon chain. They have a tendency of becoming thick in air without actually undergoing drying at ordinary temperatures. This is probably due to slow oxidation occurring at the point of unsaturation in the molecule. Examples are rapeseed oil, cottonseed oil, etc. These are used as cooking oils, and low grade oils are used in the manufacture of soap, lard, etc. Coming to drying oils spread in the thin layers over a smooth surface when exposed to light and air for few hours and set as a hard and comparatively firm film. This process is known as drying and may be regarded as rapid oxidation taking place at C double bond C positions involving various chemical reactions. Like organic peroxides are formed as a result of absorption of oxygen by C double bond C bonds. Peroxide dissociate to form different types of carbonyl compounds. Low molecular weight carbonyl compounds undergo volatilization. Condensation polymerization occurs between various oxidation products leading to gel formation. Gelatin stops further penetration of oxygen and also immobilizes the surface layer. Examples of drying oil are tung oil and linseed oils, etc. Now we can further classify the drying oils as boiled oils, blown oils and stand oils. These are obtained by different techniques which can be shown in this table, which differentiates between the boiled oil, blown oil and stand oils, and they have got different uses and applications. Now coming to an important topic of fat splitting. Fat splitting is fundamental to efficient manufacturing of all downstream oleochemicals, fatty acids, fatty alcohols and soaps. It is mainly used for production of fatty acids and crude glycerin. Oil splitting or hydrolysis is usually performed with high pressure stream, resulting in the formation of crude split of fatty acids and crude glycerin dissolved in the excess of water. Oil mainly consists of TG, that is triglycerides, DG, that is diglycerides, and MG, that is monoglycerides, so it can be splitted by hydrolysis. In industrial practice, the most widely used feedstocks are tallow, lard, palm oil, coconut oil, palm kernel oil, as well as the fatty acid distillate from the refining plant. In the splitting process, hydrolysis reaction proceeds in stages whereby the fatty acid radical in a triglyceride is displaced one at a time. From triglyceride it forms diglyceride, and from diglyceride it forms monoglyceride, and finally to glycerol. Here we can show the splitting process. TG on hydrolysis gives DG, that is diglyceride, plus free fatty acid, then diglyceride changes into monoglyceride plus free fatty acid, and then finally glycerol plus free fatty acid. An incomplete fat splitting process will result in a product which contains a mixture of mono, di as well as up to some extent triglyceride. Fat splitting is a reversible reaction. When equilibrium is reached, the rate of hydrolysis will be equal to re-esterification. Thus, the byproduct of glycerin must be drawn continuously for completion of forward reaction, otherwise backward reaction proceeds. Oil enters from the bottom of the splitter and reacts with the countercurrent water stream input from the top. The reaction is endothermic. High pressure stream is input at multiple points along the splitter to provide the required energy. Now, when in the end we can differentiate again between the saturated fat and unsaturated fats. As I discussed earlier, saturated fat contains C single bond C, whereas unsaturated fats contain at least one C double bond C. Now we take up the topic hydrogenation of oils. Unsaturated fatty acids may be converted to saturated fatty acids by relatively simple hydrogenation reaction. Let us recall here the addition of hydrogen to an alkene, which is an unsaturated hydrocarbon, which results in the formation of alkane, which is a saturated hydrocarbon. A simple hydrogenation reaction can be shown like this, where CH2 double bond CH2 plus H2 changes into CH3 single bond CH3. So alkene plus hydrogen gives us an alkane. Vegetable oils may be converted from liquids to solids by the hydrogenation reaction. Margarines and shortenings are hardened in this way to make them solid or semi-solids. In this lecture, we have read about the definition of fats and oils, distinction between the fats and oils. We have discussed in detail the general properties of fats and oils, out of which some special properties I will be discussing in my next lecture. Classification of fats and oils, then vegetable oils and its classification we have also done, and we have discussed the fat splitting and the process of fat splitting. We have also introduced the topic of hydrogenation of oils to you all. Thank you.